I'll try to go quite rapidly on the, we'll cover the bases, but I'll try to go rapidly and show you also what we can do else with the detectors, and try to cover what our activities are right now in quantum key distribution and in adaptive optics for astronomy, which brings us back to exoplanets. I never thought I would say all these words in the same kind of line when I started my career. So to the young ones, just go forward and you'll end up somewhere, most likely in a cool place. So the team here is, I'm the professor, so I don't do much. That's the joke normally. I have very good collaborators and founders, wonderful founders. Yeah. The group in Sherbrooke has a long experience in radiation instrumentation, actually, since the late, about 87, I think, we devised the first solid-state PET imaging system that was done using avalanche photodiodes instead of PMTs. And since then, we've generated 4 generations of preclinical animal PET scanners, and now brain scanners that are being deployed in Yale, I believe. And of course, from radiation instrumentation going to noble liquids, there's just a step to be done. So technically, it took 25 years until we were able to do that, or opportunity brought it to us. And one aspect that really triggers an engineer, I'm a physicist by training, but engineer by trade, is the power from moving from that field, which is producing about a square meter of detectors. That's the volume of silicon you need for a PET scanners, and going to many meters. Well, first, it's a cool challenge. Second, it's a market for a company like Teledyne Dalsan, a Canadian foundry that is developing the detectors we do. So, sometimes you're lucky, you're at the right position, and that's where I was when we started doing that. So right now, the things we are envisioning as to use the PDCs are the Nexo experiment, which most of you know is in limbo. Not fully dead, not fully alive. That's what it would translate to today. Because limbo was abolished by the Pope a few years ago. So I have to be specific. Argo is a much larger argon detector, but still, it leverages the same kind of challenges. It calls for the same kind of challenges, cryogenic single photon and really large area detectors. Anything larger than a square meter, when you come to a foundry and you say, we should produce square meters of this, it's not a unit. Okay, you were complaining about feet. Well, it's not a unit, square meters of silicon. It's number of devices. So we had to, 2 pi, you do that, and then you figure out how many wafers and how many years of productions are needed. That was a cool event with these industrial, when we were doing that on the napkin, Okay, so that's the kind of introduction of what I'm going to talk to you about. What I want to describe to you is the photon to digital converter design that we've made. In the real world, it's probably called digital SIPMs or digital SPAD systems. This is the brand we kind of tried to coin. A SPAD, a single photon avalanche diode, is a diode that is biased above breakdown. So most often you were told that this black line is the line where a diode operates, and it should not be elsewhere, because that's why you draw a black line on that board. But in truth, you can bias it at the A point for a very brief amount of time until it decides electrons decide to generate an avalanche, and then that polarization point actually moves back to the IV curve. Not exactly, but wants to go to that place. If you don't stop it from there and you bias too far, it's going to smoke. and the device is dead. If you do your things correctly, then you will quench that thing using either passive resistors or advanced electronics. And by quenching that, you bring by quenching, I mean you quench the current by bringing the bias below the breakdown. So it's a SPAD, and then you bring it, you can do that biasing cycle again. So SPAD is an avalanche diode operated in Geiger mode. Oftentimes you will see that in literature. So it's at a metastable point, and you actually actively cycle that. And from a basic point of view, in principle, this should not be efficient, because all the time you're doing this with it, well, it's not detecting. But if you do your work properly, the time it can sit at the bias there can reach hundreds of microseconds, and in very, very state-of-the-art SPADs that are difficult to produce as square meters. But in state-of-the-art SPADs, you can even reach the millisecond of waiting time. That's an eternity for the time it actually takes to do this cycle, which is in the order of at most 100 nanoseconds. So you have a long measuring time. So that's why it actually does work. Something that is, you have to move around its bias. What most of the people know about are the analogous IPMs, where you have a great many bunch of photodiodes biased at the same voltage, so they're in parallel and in series with a resistor. When suddenly a current appears, if there's no current, a resistor doesn't take voltage. There's no voltage at its ends. But if there's a current, then suddenly the resistor steals some of the voltage, and that's how a very bright team of Russian scientists devised a way to not use electronics to quench, but just use this passive resistor. But to do that and control the cycle, you don't control it anymore. The only thing you can do is play with capacitance, resistance, and the time constant. So it's a fixed system, and that's the beauty. It's simple, 2 connections, but it's its constraint. It can only do this with that speed. So this is an analogous IPMs. It provides readouts, current levels that you can transfer into voltage and discrete levels that you can use to count the photons. So that's the concept I was telling you. So you have, and normally here, what I emphasize is the fact that recall that the SPAD has, okay, it goes on that loop, but it's either biased in a quiet state or it's being quenched and cycled. So it's either quiet or triggered. So it's actually a Boolean detector. You go through an analog conversion, you get an analog current, you amplify that, and then you have to digitize again. So that's a lot of work and energy for something which initially is Boolean. And that's where the digital is IPM, which a priori seems much more complicated, and in reality is. But it performs because this SPAD says, I'm quiet or I'm triggered, and this quench says, oh, you're quiet or you're triggered. It converts that to a digital 0 or 1. You can do any polarity of the 0 or 1. And then digital processing is doing the rest. There's no ambiguity. Was there half a triggering event? No, it doesn't exist. So you're already quantized, and there's no ambiguity about that. So this is kind of the cartoon figure of what happens in a timeline in a system of analog or digital SIPM. In analog SIPM, you get the rapid rise of the signal and a slow fall out of the signal because you have the capacitance and charge, and it's an RC constant that you have to wait for it to settle down. So that's cool, easy to count. Oh, okay, that's quite easy to count. Double peak. Oh, is that truly double? 1.5? I don't really know. Okay, So that's the challenge in analogous IPM, but it's fully usable, and that's how most of the experiments today are using SIPMs. This is in a digital SIPM. So you get red pins. Well, there's no colors, but you get, timestamps, you get blimps that don't carry any information about the time. And the time that you can hear the blip or this interval can be set programmatically because it's in the digital world. So this is a first cartoon on what is one of the main advantage. It can be, with that respect, a bit faster. We chose to do that in Sherbrooke, and we didn't invent the digital SIPM. So SPADs initially were operated with electronics to quench in the late 70s. And then the Russian team, late 90s, proposed a series of resistors, which was crazy efficient and cheap to produce. And now we're moving back to the digital. So there are groups that present SPAD systems that are based on detector layer and electronics. And you have to optimize in 2D. You have to optimize which area you dedicate to the photodiode and which you dedicate to the CMOS, to the electronics. So you choose either sensitivity or functionalities, processing power. So the best thing, obviously, is to stack that. At the time we decide to do this, there were other people thinking of that and doing that, like Intel, Microsoft, small companies like that. And these two guys in Sherbrooke said, that's the best idea, so let's do it. It was plain crazy. But that's what we tried to do. So we did a first prototype that was quite haute couture, but now we can do it in wafers, and that is largely because the particle physics community, decided to bid on that technology for building larger and larger and more complex experiments. So that was a tribute to all of you. So what does the detector look like? A bit like the cartoon. So this is yet a cartoon. This is the real thing. It's a cross-section observation with a scanning electron microscope. And you have the CMOS layer. And these are the interconnects. And if you had good eyes and not on that screen, you could see transistors in these areas. There's so small shades. Transistors only occupied less than a micron on the top of the silicon. So technically, this is the CMOS. It's connected to the SPAD. So you have a SPAD volume here, which detects light that comes from the top side. There's an electrode here. The back electrode is connected to the CMOS, each SPAD individually. That's the connection. This is a trench that encompasses, encircles the whole SPAD to limit optical and electrical crosstalk. And so that's the device. And you see here what we call the PDC. So it's an array of 4,096 SPADs, all connected and summed by the digital electronics under. And these little pieces of silicon, which are actually connected here, this is air, vacuum. It stays put on the device when you saw that, when you cut that with this saw.
So where is the quenching circuit as opposed to resistors and parameters?
So in an SIPM, an analog SIPM, you would have this connection to the volume of the SPAD. You would have another connection just on the other side. This would be the common electrode. And on the top side here, this connection would go to a resistor that would go on the trenches around, and then to a common electrode. So they kind of wind it around. Here we don't have that because these transistors are actually doing the job of the resistor. There are variants where you have electronics that reads it, but there's a resistor that quenches it. So this is, it allows to spare some complexity. So it's produced at wafer level. So Teledyne DALSA does the sensor layer. These CMOS wafers are done in Taiwan, TSMC. They're sent to, they come to us, they sent to France to be cored down to the proper size, and then they're assembled in Bromont. So you end up with this wafer of devices, and so you end up with this wafer of devices where actually the pattern that repeats is a 4x4 diagram where these are all identical, and we have test structures that allow us to develop things. These test structures are the things you start dropping when you start to produce in volume. I was telling you it's done in Bromont. Bromont is the Teledyne, it's called MEMS since a few months. Teledyne DALSA used to be. Is a MEMS foundry, so they do accelerometers and pressure gauges based on silicon things, and inkjet ports. That's their main vendors. But they do advanced stuff, and they also have a legacy CCD line that actually produced the cameras that are on the rovers on Mars, and a few scientific grade CCDs and X-ray detector at SLAC and things like that. So it's a very nice company because they do large volume production, but they're yet interested in playing with crazy scientists, optimizing reaching crazy specs for 2-3 chips to do a detector. So that's a richesse that really is a good partner for our kind of things. So I'm gonna try to bring you to what we can do with the latest measurements we've done with the detectors, but to reach that, I have to explain to you what is in the quenching circuit. So here, still with this very basic, blue is the SPAD layer, yellow is the CMOS. So you have the electronic high-level architecture. It's a digital SIPM, so obviously you have a digital sum, okay? And this is an old slide because it doesn't start with the digital sum. Okay, so students should always focus their speech. I did not. Okay, so I'll start with the flag. So every time a SPAD triggers, it actually sends a digital pulse down an OR tree. So you have an OR gate with 4096 inputs, and if one of them is raised, the output is raised. So we know when something fired, but with that we lose the multiplicity. It could be 4096 that triggered at the same time. So this is a good thing to get timing, but we need the digital sum to be able to count the energy deposited. And because this was the first prototype, we also have an analog monitor, which is every time a SPAD fires, we send out on a pin a small level of current, just like if it was an analog SIPM. So that you operate that, you bias it, and you could put that on an oscilloscope, and you see like if it was an analog SIPM. So you're certain, you can be certain of what you see, and I'll tell you, even though we designed these things, it's very useful to debug. And thanks to the support of the McDonald Institute, we're now distributing this kind of kit to collaborators. So soon in Carleton, already in Triumph. So this is an FPGA board, and you have on it connected 2 small boards with 4 PDCs that can be used to make crude or simple experiments like looking at timing through wavelength shifting fibers in a neutron detector. I'm listening well when I visit, you see, Philip. So this is what we're trying to do, get other people to play with it. And I say play deliberately, because right now it's more playing with it and learning how to do. But rapidly we go to serious business. I'm going to show you this slide, which is one of the main advantage of a digital SIPM, if we compare to an analog SIPM, is that in this design, we sum all the SPADs together. So it's not a camera, in short. You cannot get an image out of this thing, or very cumbersomely. But we can deactivate each of the SPAD or activate only one. That's how we can make it a camera. It takes 2 hours to take a picture, so you don't want to do that. But the idea here is that we characterize the dark count of each of the SPAD on this, and we plot it in a color scope code. And all these are the same data presented in various formats. I'm going to stop on this one. This is the ordered population. So we ordered from the lowest dark count to the highest dark count. And we clearly see one main population, which has a very low dark count in the 1 count per second per device. And we clearly see that if we only take the average, like a normal analog SIPM would do, because it cannot turn off things, then you would get 26 times more dark count out of that. In low background experiments, okay, we get the temperature for free, but you guys are crazy on specifications. So you'll always figure out a way where the dark noise has to be 0. We will not deliver, but we can do our best to do that. So, so the trick here is something you cannot do with an analog design, is by shutting off about 5% of the sensitive area, you can get 26 times more on signal to noise. Normally, that should overcome the loss in sensitivity in sensitive area. And that's a main feature of the device. You have a fixed area, but you turn these red dots off, and now you have 26 times less dark count. So this is, I think, an easily understandable aspect of the device. So we only get a sum, but we can help that sum to be cleaner. The timing also is a nice thing. I could start with this one. So by measuring the timing precision of the signal that we get from the flag. So you take a femtosecond laser, you filter it until only 1 shot every 100 shot actually is detected. So then you get only below 1 photon per event, so that you're certain you're in the regime we call starved, photon starved. So there's only 1 photon that triggers it, because we want to measure single photons. So that's how you have to measure it. You repeat that 100,000 times, and you get a distribution of the time delay that you get from that measurement. And right now in this system, you get 169 picosecond timing resolution on the detection on that wavefront. So that's about 10 centimeters. Yeah, 10 centimeters at the speed of light. Centimeter-ish, yeah, 5 centimeters at the speed of light. So this is quite interesting. Can it be done for 200 square meters? I doubt. Each device could. Doing that for a large system is another challenge. The other thing, I told you we cannot know the address of the device, so we looked at the uniformity of the time response. And the don't look at the average here, these are all preliminary, as it said. So the deviations of this jitter from one to the other, the registering of the proper time, not in sense of relativity, but I meant real time, is of only 17 picoseconds, which is negligible. So this system, if you have very few photons, it actually can give you a timing on the order of 170 picoseconds of the time of arrival. If you have many photons, then you know the first photon and the others could be blurred in the rest, but you know the count. I'm convinced clever people playing with the detector will figure out ways to improve timing far below nanoseconds and provide new discrimination methods, for say, in the field.
So,
Hmm?
okay, what's the timing resolution? What, time per pulse, I guess, because that's the resolution, right? How well can you determine, you know, you have
So-
photons, okay, or they
Yeah.
they overlap?
So that's interesting question. So the flag, we can set its length down to 2 nanoseconds.
Yeah.
So normally you should be able to see photons that are triggered, that come in every 4-ish nanoseconds. Nanoseconds. The timing, the time frame at which we can sum the whole thing, that's 10 nanoseconds. So all of this registers. If there's not too many photons, you can do something with that. And even in the case where there is a lot of photons, like in PET imaging. So you get a high energy gamma or annihilation photon. It generates 2,000-3,000 detectable photons on the detector. So that's a lot of photons, but you're interested in the time of the first ones. So actually, you see the first ones, and after 10 nanoseconds, then you don't see anything, but then you count in an old-fashioned way. And then you get all the information for the energy and the timing of that thing. So this is an example of the kit we're distributing, being used with 4 at home, with 4 LYSO crystals for PET image that would be used for PET imaging. So we're operating the 4 PDCs at once. Here we turned them into cameras, and we looked at. Oh, by the way, LYSO is lutetium yttrium strontium oxide, the silicon oxide. The lutetium-176 has a beta decay, and it's 2% of natural isotope, so you can't really get rid of that. So it's actually a nice feature because you don't irradiate the detector, and it still shines in the dark. Okay, so we placed the detectors and we turned 1 pixel at a time in camera mode, so it took 2 hours to do that. But we see the crystals where they're placed. In the normal world, people doing scintillator work, they buy an SIPM of a fixed size, as close as they can to the crystals they have or can manage, and they place it on there, and they get the total count and response from the whole thing. In this detector, I can turn off all SPADs that are not under being exposed by the information I want. And in this case, because it's a 4x4 millimeter crystal on that 5x5, you save 30% of noise. And that's above what I told you before, which is 26% better if you shut off the dark ones. So this is the exact first picture we had. We were so crazy disappointed. It works. We should have been very glad because it was not uniform. And actually, when we dismantled the thing, we actually saw the perfect mapping. We just were too cheap on the grease, the optical grease, because we didn't want to break anything. So we did it again, put more on it, and it was perfect and uniform coupling. So we kind of discovered many things of that, and you can know much more than in an analogous IPM if you're coupling correctly and things like that. So we shone radiation on that, and this is a cobalt-57. It's an electron capture emitter, and it's the excited mode that gives the 122 keV. That's the extent of my understanding of this. And you have the main peak here, and it's actually a quite low energy kind of spectrum, but this is the first thing we got of our detector. And this is the first measurement. Okay, it's not exactly the first, but you know, the first day, the first hour. It's made with the analog monitor, so that's not yet a real digital readout. So we looked at the analog monitor that mimics the SIPM because when you go through a computer, you can mess up in the computer. When you go with the analog chain, you put an oscilloscope, you see the cable, you know if you're connected, you see something. Okay, so we did that. We see the signal, we see the saturation because there needed to be a gain in the system, an analog gain. But we were already very glad to have 30-ish% of energy resolution with that lousy emitter. It's known to be lousy for reasons I do not know, but this is my pet people, my positron emission tomography people that do that. So we converted every photon into a 1 microamp signal, and we measured that. This is a cool feature. Now, instead of just putting 1 microamp, this is useless, but it's cool nevertheless. We asked the system to give 20 microamps, so much better transformation from the digital 1 to current. And then we measure it analog wisely. And this is what you would see if you were to have a non-existing analog SIPM. You would see finger plots like that because some events would give you 10 photons, others would give you 20 photons, etc. And these would be quantized because it doesn't give half a photon. So that's what you would expect. But you never get that in an analog SIPM because under here, there's a huge analog background that you amplify, etc. So the features you probably don't yet appreciate much is the level at which it goes down there. It's plain crazy. And you see up to 60, almost 70, if there was signal there, we would still see it. But that's not in an analog mode. We want to use the detector, but it shows like how crisp it is inside. And we skip the analog conversion, and then we get the digital sum out. And that is easy to do with the 4 at once. We get the 4 signals are operated at once. This is still the setup. And with the cobalt 57 still, and you see the 4 peak, the big peak here. And there's no saturation at 2,500 photons because it doesn't happen. There's no gain. The system is not saturated before that. We still get 30-ish something % in the digital version, of course, because we never do any analog mess in between that could deteriorate that. And then we were suspicious. We wanted to understand why the shapes were not the same. And we pondered and pondered, and someone opened the box, and the source is on this side. So, of course, these two shield the other one. Bingo. Okay? So then we were content. We changed the source. Now we have a more energetic 622 keV, and this peak has 10% resolution. This is among the best measurements you can do with an analog SIPM with these crystals. And at room temperature, and we don't know how to do that kind of thing. This is just my best electronic engineer putting something he never handled before, a radiation source. He was trained. And then you get that. Of course, it's complicated to get there, but the system is more, in that sense, reliable. And it's difficult to carry to a group until you actually put your hands. So if you want to play with the devices, just call us. Yeah. So this is, you hear in my voice, my hype about that. One of our good supporter is the Oak Ridge National. Where is that? Oh, I'll keep that. Okay, that was warm. Is the Oak Ridge National Lab, for which we are developing, with whom we are developing neutron detectors, associated particle neutron detectors. I'll skip the details about that. But for that, we need to make tiles of systems. Who would like to have tiles of these? Many. So it's nice that this neutron work there brings us to to focus on producing large systems. For now, part of the coming years, I already have a few students working on making that into a single chip that would be on the back of a detector. This is what with Oak Ridge we're supposed to replace. These are PMTs looking at scintillators for a square foot detector just about, and a neutron detector for neutron imaging. They want that for non-proliferation inspection in ports and things like that. So this is not ours yet, but this is the concept where we want to go. And funnily, we were discussing this structure with Guillaume this morning for neutron detection and things like that. I talked to you about what the detector I showed you and we are testing right now is the low energy, the low power consumption version of the detector. It does minimal processing. It makes a sum. It delivers an OR gate. So it's the basic thing. There's a lot of configurability. Every day we find a new way to, every second day we find a new way to do something we didn't plan on. But there's also applications which need much more than that. And this is the architecture we devised for and tested this architecture without SPADs or with limited access to SPADs for other type of application like medical imaging. So again, this should be half familiar. It's a chip. This is an array of connections on which we would connect the SPADs. Here we cheat. This is a CMOS chip, but we hid the SPADs up there so that we have real signals for the readout. And this is a PET imaging pixel of 1 square millimeter. This is a quantum key distribution variant of the same with a small array of SPADs. This is suboptimal. These SPADs are very lousy, like 2% sensitivity and 1 million count per seconds in noise. But it provides a signal that is a signal of a SPAD to electronics, and that helps us to prove it works. And under this area here or under there, for each SPAD, or for each four SPAD, we were able to put a time to digital converter, which has a precision of 20 picoseconds. We were able to also hide in that area. We don't use the rest of the area. Hide in that area the processing. So you take timestamps, you can order them, you can make a weighted average of the first photons. You can try to remove dark noise, and etc. We do that all inside the chip so that, for example, in PET imaging, what you want is the time at which the annealing photon came in, the 511 keV photon came in. You want the energy locally to make sure it's a 511 keV, but you never carry that outside of the chip. Right now, you don't need to. Right now, we carry everything outside of the chip because someone has to decide what that was and at what time it arrived. But with the processing capability that we embed, we can do that inside. We can know the energy, and we can figure out one timestamp for the 1,000 photons that came in. And by doing that, then you have a much simpler output of data, and then you can increase the rate at which you can do that. And that's needed for applications like PET. And that kind of processing is something that might be needed in particle physics for accelerator kind of application, because the rates can be very crazy, and you would like to only save data that is relevant. But also in low background, because if you have 200 square meters of stuff, if you don't want to have James Bay providing the computer that operate that right on the side, we need to move SNOLAB to James Bay. Complicated, isn't it? So we can do some processing in there probably. So that's what we did. And now in the last few minutes, I want to show you some applications of that version, that advanced version of CMOS that we're developing. So right now, this chip is being turned into a 5 by 5 millimeter, so 16 times more than that, in the same form factor as the device that I was talking to you before, so that we can mate it with the same SPAD array. That's the concept. So one of the application that I figure PET imaging is something you already kind of know. So you inject a radio tracer, it emits a positron, there's annihilation, 2 photons go out collinearly, and you figure out that line by detecting those. If you have time of flight, you narrow that line to ideally a centimeter, and that's the holy grail of that modality. If we were able to have something like 50 picosecond timing resolution on the line of sight, you could have direct imaging. You could look at the image being formed on the screen. Right now, you cannot do that because you get a series of lines and you have to invert the matrix to get an image. And that's half of the time you're waiting in the room if you've had a PET scanner, which I don't hope for anyone. So having access to very rapid, very precise timing is important in PET imaging. It could allow us to reduce dose. And in time of flight CT, so computed tomography, you have a X-ray source rotate around your body at a crazy speed. There's a reason why it's hidden. It's like many tens of times per second. It's a half a ton that goes like this around you. You probably don't want to see that. And your detectors there, they detect when photons, when X-ray, it should be animated. Yeah. When X-ray photons are emitted, oh, it was a white line. So there was a white line that went through, but in the body at a certain point, this line that should be detected here was content scattered to another detector. So this is the true signal that you don't see, but this is a noise signal. And in CT scanners right now, they're almost at the same level. They managed to operate it to reduce the dose at almost the same level and get an image. So how could we remove this red line here? Well, if we can measure the time with a precision below 100 picosecond, then on a human size and 2-meter type of travel, you could distinguish between the true direct line, the ballistic photons, and the diffused photons. And that would allow to change a lot this modality, reducing dose. So this, you don't inject radio tracers, but it's still one of the highest dose you can get on a medical imaging adventure. So this is a very important new field being developed in Sherbrooke, time of flight CT. There's also quantum key distribution. And so that's really not in the realm of particle physics, but it's still counting photons because in this case, the information is carried by just one. So in our field, we're kind of lucky because we might have a dark particle generating a few hundreds of photons, tens. It's at least not just one. Okay, so you have to measure it still, but that's there. In quantum key distribution, you have to get the photon. The easy part, the cheat in there, is that you know at what time it should come in, because it's emitted somewhere, and it does carry at the speed of light. So if you know the path, you can determine with sufficient precision, in principle, theoretically, when you get your photon. So in one of the implementation of that, you actually transform through 2 interferometers, you actually transform polarization information, quantum information that is stored in polarization, into time. So you send it into an interferometer, and then these versions interact. One goes on a long path, the other one on a short path. So you transform polarization quantum states into, it's very faint, but into time delays. And this is our chip being measuring single photons and giving you the time at which it arrived. And through this interferometer, double path interferometer, you see that it arrives mainly early, middle, or late. And in there is quantum information to be, if that was truly quantum information being transmitted. It was not. It was a demo. But there would be information in that timing there. But again, like in PET imaging, we're not interested in knowing when it is precisely. We want to know, actually, if it went on the long path of the interferometer or on the short. So we want to know if it's early, if it's late, or if it's in the middle. So the information is much more digital than a full time. So the timers in the time converters in our chip allow us to do this processing from here to there. This is real data. So from real time into which bin did the photon come in, most probably. And from that, you've just sifted 16-bit of time precision into, well, that's 3 bits of information that you want to carry out. So that is important if you want to increase rates and find application, real-life application for that. So why is that moving? Is because, so this was not in a low light kind of setting, but it counts single photons nevertheless. So the information is half true to what I told you. And someone is playing with the interferometer length just to sometimes make it even when it's all even, and or make it longer. And the time difference here is not written. Used to be written. It's about 100. It's just below 100 picoseconds. So it is path. It is a path that is rather change that is rather small, and that is an important thing if you want to, interferometers come in all sizes. Think LIGO. It's cumbersome to carry. If you want to fly in a satellite with that, you would like that to be in a solid state. That's kind of a jeu de mots. By reducing the time resolution, by increasing time resolution and reducing the time difference between the information, you can shorten that and then get transportable interferometers. So this is the case. And because each of the SPADs has its interface, the guy was also, Simon was also playing with the position of the beam on the detector. So now we see timing at 20 picosecond resolution and the position on where the photons arrive. So this is a cool tool to work with. And the last example I wanted to talk to you is rapid wavefront sensing. And it's linked to quantum key distribution. That's how we came into this thing. If you want to communicate with someone in free space, there will be wind in that path. So light will go like this, and you will have to stabilize with mirrors, adaptive optics. You'll have to stabilize that channel. So the conundrum is you want to catch one photon, but you would need a laser shot to be able to control that positioning. So many people are trying to figure out a way how to line up with as few photons as possible. And it so happens that's the same challenge of trying to filter out an exoplanet from a bright star in a very remote setting. So people that are trying to do that, they want actuators and adaptive optics that can operate in the kilohertz, not the hertz, the 1,000 hertz, 10 to 20 kilohertz, so that you can correct the atmosphere variations at a much higher degree than what is possible right now, and then see fainter objects or stabilize a channel. And one of the ways to do that is use time. This time in astronomy, we don't know when the photons come in. So we need to figure out how to do that. What the astronomers do, they use faint stars around the environment they want to look at. And they use those faint stars which are quite bright by comparison to the exoplanet, to track the atmosphere and try to stabilize it. But the planet doesn't choose its target stars around. So the catalog of observable planets with this technique is limited by the availability of bright enough dim stars in the environment. Sorry, that might not be clear, but it's okay. You have to have it bright enough to see it, and that limits the number of candidates. So we need to go faster and be able to measure stars, look at stars that deliver about a photon a second. So back to 1 photon at a time. So with our detector, we certainly can do both. And Simon Carrier, one of my students, had the idea so they're using, that's it, in the Herzberg Institute on the Victoria Island. It's on the Vancouver Island in Victoria. That's an NRC facility. So they use a pyramidal beam wavefront sensor. Essentially, you shoot the light on the tip of a pyramid, and because there are 4 faces, it generates 4 images of the beam, and it allows the light to interfere. You allow interferences in there. But it's very difficult. It's very difficult to keep the light exactly at the tip. So what actually people do is every millisecond, they rotate the beam on the 4 sides of the prism. That proved to be more stable. So you get in time many images, mainly one at a certain time. You have this one because the beam is on that face. When the beam is on an edge, you get 2, etc., because the beam moves around. So in a slow time frame, milliseconds, the image moves around. For us, it's very easy to actually measure single photons at a rate of 48 kilohertz. That's actually more than they ask for. So we can measure the evolving picture tracking this beam, and actually it shows that instead of blurring all the images, because they integrate essentially in normal times, they use a CCD camera, so they integrate over a millisecond. So you get a blurred image, whereas because we have good timing and single photon, we can get, these are cartoons of course, but you can get an image for each relevant time frame, and that is more informative than the general average. So that's how essentially you can link with a single kind of type of detector, PET imaging, quantum key distribution, exoplanet research, low background radiation, in the same family of devices I have the pleasure to play with. So that's kind of a conclusion, if you didn't figure that. 6 minutes and 20 seconds.
Questions?
Head scatters and lower doses.
Hmm?
Compromise. You want very fast timing for magnetizing evolution, which means you have to get rid of the crystal gauge on the film. That's why you look at only the first few photons.
Yep.
You want to see the first few photons, you need a lot of photons. And that sounds like the dose goes up, you get a lot of photons, so you can get right to the right edge.
No, because there's the transfer. So you have the 511 keV. This one generates thousands of visible photons that you want to measure. So these are the fronts you want, because what you actually want is the time of interaction of the 511 keV inside the crystal, and that is mediated by the visible photons being emitted there that go to your detector. So I said no, but you're right that the challenge lies in the scintillation of that crystal, the transport of the light to the detector. Right now, that is the crux of these systems. Scintillators, they barely deliver something below a nanosecond capability. And they have long tails, typically in the tens of nanoseconds. So that's where we are. So right now in this community, electronics, analogous IPMs can deliver very good things. Presently, commercial full body scanners use 200 picosecond resolution, 200 picoseconds, so that's almost the size of the human. So you know if the photon came from inside. That's already good. And middle or not. So there are many things they can do with just that information. But it's the crystal that are limiting to go further. So there's a whole community looking at meta crystals where they combine plastics and semiconductor nanodots that emit very fast, and so you get electrons, secondary electrons from the 511, transfer that energy into a cocktail of other effects, some being fast, and then you get those. Yes.
So I think there's some work being done on well, the liquid.
Scanners, yes.
The advantage there would be what?
It's an old idea, or no, it's an idea that has been long discussed. It hasn't yet proven fully functional. I don't really understand why in details. There's always, the medical field is very, very refractory to any changes. So introducing someone in a cryogenic kind of tube, it can go to there, okay? But there is also the fact that it is a scintillator. The problem is you need one of the issue, you need quite good volume of detectors of the scintillator of the liquid because penetration is longer. You want to have all that because you need to know if it had a Compton before it was detected. So there are many things, the devil being in the detail, that catch you up from the first numbers. So there were people in Vancouver, I believe, SFU, I think, are still with the idea. There are French groups on the West Coast in Nantes that are looking at this. And every once in a while, we write that in argon detector application, that we might be able to turn that into timing could be a key. Maybe a better photon detector does solve part of these.
Just a quick question. So you had a great result that you showed when you bend things in like 20 milliamps, and then you showed like that you're not limited by the 50 so you're saying like getting photon counts. Is there a way forward to cut down on whatever is giving you still that 10% energy resolution spread and just get really tight energy resolution detectors?
That's a very, very good question because I really don't know. I yet have to understand. So these are the first measurements we actually, you were referring to that. These are the first measurements we actually make of those. So I need now to understand what's the physics behind the width of that interaction. So I did something in the train coming because some on Teams there was a guy one of my team members posted a table. So I took the resolution and the energy and I tried to plot the Poisson dependence. It doesn't work at all. So there is still a big contribution out of just the statistics. So that's the next thing I'm going to read, maybe on the train back. Because that's a good question. I would like to show outstandingly the superiority of the digital approach. And I was hoping to get the straight line, and fortunately I didn't say that before showing it was not there. But we're fishing for that. You see, one of the experiment we're going to try to do next week, or when we come back from the conference, is on the same area, we can turn on, let's say we decide to turn on 1,000 SPADs. Then we can also turn on these SPADs in with a SPAD in between, not turned on. So we can spread it larger. So that would eliminate crosstalk on the detector side. Is that important? So we can show that. It's analytically analyzed from analogous IPMs. We could do the same measurement with reducing, so without moving a crystal, with reducing the number of SPADs. So you should go down, you should go down the Poisson. So the Poisson dependence now should, the width should scale if Poisson is dominating. So these are toy experiments that I lack the number of people to be able to do these days.
You know what the internal crosstalk fraction is?
Sorry, the crosstalk?
What's the internal crosstalk?
Yeah, right now we're completing the measurements. It's in the 10 to 15% right now. And I kind of told you that the trenches were to isolate optically, but they're almost transparent because they're silicon. So they do a part, but we know technically right now we cannot, but in a next generation we're considering to do that. It's a technical problem.
Thank you very much, Serge.
Merci, Guillaume. Thanks for those online.